I'd like to thank Josh, the Methuselah Foundation, the NSF, NASA, CASES, and all the people that brought this meeting together. The impact of bringing this talent together and us discussing the future in this industry, I think, cannot be underrepresented. And I actually am going to come up with a prediction today. I predict in 25 years, historians will look back at this event and the events related to it and credit it with bringing organ or tissue and organ engineered products to the patient 5 years faster and a savings to the economy of hundreds of billions of dollars. It's truly needed. We talked a lot about the problems with organ transplants right now earlier today. We also have the problem of the increased age population. So the supply is going down, the need is going up, and it's critical that we work in these areas to solve these problems. There are many ways that we can solve this problem, and bioprinting is one of them. To tell you a little bit about how I got into this, my career is all over the place. I started off in robotics, moved to cardiology for a bit, then created and eventually sold an IT company before I went into academia, and was working primarily in regenerative medicine, working specifically on creating microvascular conduits ex vivo and keeping them alive for a longer period of time. More recently, I was CTO and later president of a company working on bringing biofabrication technologies to the clinic, and this company now is on a fast track to move a cell therapy to the clinic and start hopefully laying some of the foundation for future companies in this space. So what are the goals of biofabricating organs? And what are the challenges in this area? Well, there's many, and we'll go over a lot of those today. But the ultimate goal is, of course, the creation of a functional tissue or organ that will replace the lost function in human patients. This is being done currently by the donor organs, which we've talked about a little bit. We don't have the supply of them that we need, and there's a lot of negative side effects to those organs going into the patient, not the least of which is anti-rejection meds they have to take for the rest of their lives. Research continues to look for new methods to solve this problem, and there's a lot of great ideas out there. You know, one of the challenges that Dave mentioned last night, we must move from not only the big R, the research, to the big D of development, but I would like to introduce another letter, which is a big P, which is a patient. So not only look at developing these organs, but let's start to think now and start the conversation now of how these organs will fit into the clinical workflow to help the patient so they can go on with their lives and have more quality life years ahead. So how do we engineer these organs? There's a number of ways. We talked a little bit this morning about the D-cell RECELL method, which has a lot of promise. We have the in situ formation from cell aggregates to possibly generate an organ or organoid function, both in vivo and ex vivo. But today I'm going to concentrate a little bit more on the bioprinting. Bioprinting, in a nutshell, is taking cells and cell aggregates in bioinks and putting them in 3D space. What we're really doing here is we're creating initial conditions for a biologic experiment that we have a defined outcome from. We're trying to create organs or organ function by doing this, but really, you know, and one thing that should humble all of us is that the cells are doing all of the work. We're just trying to create the conditions to where those cells will become and provide the function that we need. To start the conversation, I sent out a brief questionnaire on Friday to the bioprinting committee. And Josh, I'm hoping you can get the link out to everyone else here, because I really like to get input from everybody on this. It's about a 5 or 10 minute questionnaire, but it's going to give us an idea of what people are doing and how we might possibly work together. But to go over some of what we found so far to help spark some conversations in these committees, I asked what type of bioprinters people are using, and we got a range from homegrown to commercially available ones. Over the years, we're starting to get more commercially available printers out, and the printer is basically a tool for allowing us to do our research and our design, and I think that's encouraging. What are people using them for? Some of the answers I got were bone regeneration, vascular conduits, for teaching, for creating bioreactors, and for muscle. Some of the accomplishments, which I think is an important thing, and I want to hear from everybody on this, the micro accomplishments are the mega ones. Some of those are that they've created air ossicles, iPSC-derived spheroids with capillary-like Primoria, high cell viability using multiple materials, contractile muscle, and half-centimeter constructs surviving implant for a period of time. How are bioprinters helping you with the research? And this might be food for thought for some of the people that aren't using them as well. They're able to more rapidly accomplish their goals, added construct complexity. They're able to increase the scale and size of the tissue constructs, precise placement of cells and aggregates. And one of the ones I found interesting was characterization of functionality in more complex environments. So by design, you could probably characterize better because you're controlling the environment. Long-term goals we've talked about, and it's organs in humans. But one of the other goals, too, that was mentioned was creating constructs that could be used in areas where you might not have options, such as in low Earth orbit. What features we like to see: environmental chambers, melt electrospinning and writing, better resolution and better control over inks and spheroids. What features did groups want to see in the bioinks? So a lot of us working in bioprinters, we know that the bioink is really where a lot of the science is. And I was curious as to what, where people were going with this. Major features that they want are better fixation time, universal ink for any cell type, easily changeable matrix types with different cells, including human matrix. And I'm going to go briefly over the rest for time, but asked what cell types people were using. I got an average of 2.5 unique cell types per response. So cell types are all over the place. There's a lot of different epithelial classes of cells that are used, endothelial, of course, really all over the place. What type of bioink base are people using? 3 unique responses per recipient on this. It's all over the place, from the natural matrices, fibrin, collagen, things like that, to PCL and synthetic ones, and now people are starting to use store-bought bioink bases. And one question that would be interesting, I'm not going to tell you what people said so far, but one question I had is, when do you think we'll start seeing first-in-human applications of the biofabrication that we're doing now? And got a bunch of interesting numbers on that. I like to see what other people think. But overall, suggestions, what people would like to see in this roadmap, and one of the items was more of a consistent language. We deal with a lot of disciplines in bioprinting, from biology to medicine to engineering and physics. We want to see uniform terminology so we can all be talking the same thing, and a move from doable to sustainable to expandable. So thank you, and take any questions.
Why don't we hold questions for the discussion, and we'll go into that right away. So as we get into the discussions, I'm sure you'll be able to talk with Scott